calculation. I didn't get into the derivation part of this because it's pretty long, but if I had mentioned that if anyone wants the derivation, I can send it to you separately or I can explain it to you separately. So what we had done was the analysis of the light curve for hat P20b, and I had asked you to calculate these values for WASP-84b. That's another exoplanet. So the questions posed were to calculate the change in flux and to find the radius of WASP-84b, that is the target exoplanet. If the radius of WASP-84, that is the host star around which exoplanet revolves or transits, and the radius of WASP-84 star was given to be 0.74 times the solar radius. So you had to take the constant solar radius and calculate it based on the formula that was given. And you had to always also using the radius find the volume of the target exoplanet and also of the host star. Now the discussion was to find the Jovian radius and to compare the size of the target, that is exoplanet, in terms of the Jovian percentage. And the answer expected was this, wherein we had flux at rest. Here you can see we have a predicted start of the transit and a predicted end of the transit. So at the start, how much is the flux marked will be your flux at rest, that is 1 in this case. So this is not accurate to the point because we are taking a visual analysis to see how close we can get to the accurate points when we do it on a software or a tool. So on a tool, or especially if in AVSO in itself, when you take the light curve plot, you will be able to simply keep your mouse on each point and see how or what the coordinates are for that point. So you will get how much it imposes towards the flux. You will get the exact coordinates, right? So here predicted start we take as 1, and if you go down you will be able to see somewhere in between 0.98 and 0.99. So you can take it close to 0.985 or 0.984, so we expect somewhere around that region. So when you take it using a tool, we observe that it is 0.984, but when you visually analyze it, it is 0.985, so you will get an approximate value. So we take the change in flux, that is the flux at rest minus during the transit. That is the minimum value up to which the flux goes down during the transit, right? So our flux change would be 1 minus 0.984. So you get around 0.016 or 0.015, depending on the value, whether you have taken 0.984 or 0.985. And then we had the radius of the star, host star, that is WASP-84, given to be 0.74 of the solar radius, and the solar radius is given to be as a constant, that is 695700 kilometers. And we expect you to multiply the value to find the radius of the star. And we have a formula here wherein the radius of the exoplanet is equal to the product of the radius of the host star and the square root of your flux change. So with this simple formula, you try to find the radius of your exoplanet, which should come around to this value. And then you use the simple formula of finding the volume of a sphere, because exoplanet could be nothing less than a sphere. So we consider all the other, we neglect all the other factors, and we take a simple sphere volume formula, that is 4 by 3 pi r cube. So here for r, you take the radius of the exoplanet and you find the volume of the exoplanet. Similarly, you find the volume of the host star because you have the radius of the host star as well given. So this was what was expected. And for the discussion question, we were expecting wherein Jovian radii is nothing but the radius of Jupiter planet. So you take the Jupiter planet's radii and you try to compare the radii of both Jupiter as well as your exoplanet to see how close or in what kind of vicinity of Jovian radii do you find the exoplanet's radii. Now, since it's somewhere around 100%, as in the HAT P20b is calculated to be 1 or 2% of Jovian radii, and WASP-84b is considered to be somewhere around 91% of Jovian radii, we can clearly see that it's somewhat of the similar size. Either more, in HAT P20b, we can see it is slightly more in size than the Jupiter. In WASP-84b, we can see it is slightly less in size than the Jupiter. So since it is somewhere around 100% and it's close to that size, we consider or we assume the properties of this planet to be similar to that of our exoplanet. So in that case, since we know that Jupiter is a gas giant, we assume this is also a gas giant. Then we further proceed into our various other researches and analysis, and we see if any of our findings or research points are being contradicted due to this assumption. If these assumptions are not contradicted, then you can ascertain the fact that these assumptions are right. If it is contradicted, then we start from that contradictory point and then we try to research further. Okay. So let's say if the size is somewhat less than 40% or 30% of Jovian radii, then we go on to find to compare it with that of Earth or any terrestrial planets. And if that came around the same, then we could assume that it's a terrestrial planet and maybe it has a solid or denser core to it and denser composition to it. So then we could go on to test what could be the elements present there. We could take some spectrometrical analysis based on that and see what the composition of these could be. So this was the idea of this project, to give you an exposure to these kind of visual analysis questions, because we are not in a position to collectively do any tool or software analysis. So this could be an easy approach for you, just to give you a kickstart to what you could be doing further with the project. So this is it about the last session. Now we'll continue with our today's session. So I'll stop sharing and reshare.
भैया मोबाइल नंबर 888 43
Hope my screen is visible to you all.
453
Yes,
गाड़ी
sir.
नंबर
All right. Okay. So this sort of goes back into our old one of the sessions that we took based on what young outbursting stars are. So today we'll be looking at
Simple,
the
है ना?
light curve analysis of the young outbursting
मालूम है
stars we
destination?
got. And this is through a citizen science
मोबाइल है
project called HOIS, or Hunting
मैप
of
ओपन करिए
Outbursting Young Stars. And this is a project that can be completely done remotely as
उधर वो बाहर
well. So I highly
उधर बाहर
recommend, if
वो चेयर
anyone
में
wants
बैठा
to
है
know
ना,
more about
उनको
this
बोलिए
project,
बता
please
देगा.
contact me and
राइट
we
साइड है,
can
एग्जैक्ट बता देगा.
set up a remote project idea about it as well. So moving on, I'll give you a brief
नहीं, आने
on
के बाद
what
कुछ नहीं
we
दिखा ना,
will
बस
be
गाड़ी
looking
नंबर हो तो गाड़ी
into
नंबर
for
बोल.
this. Give me a moment. I think I'm sharing it wrong. I'll just reshare it. I'm sorry. All right. So, um, yes, the screen is visible. All right. So moving on today, in today's session, we'll be brushing up on a few topics from outbursting young stars, as well as we'll be looking at some observations and discoveries made during the observation or during the project. We'll be discussing the results and discussion of light curve analysis, and we'll be having a very brief discussion on the project. So, just to take you all through what these were, we had already discussed in the first part of our workshop where how stars are formed and how young stars are meant to be perceived, and how star formation in general is. So we have a dark cloud wherein a lot of clumps will be formed, then it starts rotating or spinning very fast, that we'll have all the denser particles or the clumps accumulating to the middle, and that's called a prestellar core. Then we'll have a protostar wherein there are ejections happening, the extra energy is being ejected to the outside from the core, and you will have all the gravitational forces being attracted towards the inside, and you will have a proto disk formed around your protostar, that is the core. Then we have the pre-main sequence star, wherein all the gravity is pulled in and your core is stable. So you just send out extra energy towards the outside, and you have a main sequence star with all the extra energy, as well as some loose particles, some unstable particles sent outside, and these particles start revolving around the star. So this is the most brief way I can give you about a star formation or a solar system formation. So yes, we had some outbursting young stars shown in the picture, as well as accretion disk discussed in detail. Can someone tell me what accretion disk means, or if you remember the term from before? Can someone tell me what accretion disk is?
It's a disk of matter surrounding a very fast rotating stellar object.
Yes. Does any sort of process or phenomenon take place in the accretion disk?
Formation of protoplanets.
Hmm. That is primarily due to the unstable particles that escape from the accretion disk.
Black
Within
holes?
the sorry,
Black holes?
yes, that is at the depth of an accretion disk, or rather an implosion of accretion disk. Any other processes that is taking place in the accretion disk? Any energy transfusion or any sort of
accumulation accumulation of matter to create stars and planets.
sorry, come again?
I mean the matter. I mean the in the
Mhm.
accretion disk, the over time the matter will accumulate into clumps, eventually
Yes,
forming kernels for stars and eventually planets.
right. Yes, that's right. Yes, but any sort of energy transfusion or energy escape or energy intake or force intake, anything of that sort is happening in the accretion disk?
गेट कॉपी ऐसे
All right. So accretion disk is primarily where all the
बेतुले
internal core energy is
हाँ
escaping,
ये
right? And it
एफ
is
का ही
also
बिनता
at
है
the same time
स्टेम
being
तो मालूम ही
crushed
ना
by the gravity from outside. So there is an inward gravitational force as well as an outward energy escape. Okay. So a lot of electrons are being sent out, and a lot of nuclear reactions are taking place at the core of the accretion disk. So all these accretion disk is like a critical boundary from which all the phenomenons, all the process, all the chemical reactions are taking place. It's like a mediator between the core and the outside, right? So this is the primary idea of an accretion disk. But yes, any particle that is being unstable and that is escaped the accretion disk will later on form other celestial bodies. Now, young stars are significantly unstable and they have a lot of fluctuations in their brightness. Can someone tell me why this happens? And the fluctuation in brightness is simply put as outbursts, or there are like sudden burst of energy or sudden brightness that you see. In other words, you could call them flickering or twinkling. So why do you think this happens in young stars particularly?
Because they're unstable.
The accretion disk temporarily gets more luminous than the core
Okay, why does that happen?
because of the viscosity and the friction.
Okay, viscosity. Oh. Is
I
there a
think the
name to this
temperature.
process? Sorry, Samali, please go ahead.
I think temperature is also important for this. Temperature differences.
Temperature differences. So you believe there are sudden drops in temperature?
Yes, kind of. Certain changes in temperature can also occur.
Okay. So if there has to be a
Can it
visible
be because
effect.
of
Sorry, come again.
yeah, go on.
Yeah. So no, I was just posing the question where if there has to be a visible effect to the temperature variations, then the temperature variation has to be drastic enough to see those differences. What do you think, Samali?
Yes, I think the near the accretion disk, it's hotter. I mean it's hotter in near the center, but it's cooler at the edges. So that's why.
Yes, yes, that's a very interesting
Is
point
it
to note.
because I mean is it
Go on, go on.
yeah, I was saying is it anything related to that since the stars are young, their core will also be young and it will not be formed of iron and all. It
Mm.
will be more energetic
Yes,
and
it'll be more energetic.
there will be release of much more energy.
Yes, as well
Yes,
as
the
they
core.
have a lot of active
Because it is
reactions taking
unstable
place.
right now, it tends to be stable. Yes, yes,
Sorry, come again?
correct. I'm saying that it is because everything tends to go towards stability, right? So
Right.
the core is unstable right now.
Hmm.
So yeah,
So
there
yeah,
will be energetic reactions and all.
mm, okay,
Yeah,
I
yeah,
get your
that's
point.
okay. I mean,
Yes,
this
yeah,
was something that I thought.
yes, I get your point, and the point is absolutely right. So as the stars are younger, they are more unstable to the core side. So in the core of the accretion disk, what happens is there are a lot of ongoing reactions that take place, that these a lot of explosive reactions that is taking place inside that matter is making it very more challenging to be stable. And there's also a lot of outbursts of energy because it is just pretty young and it's just undergoing through raw reactions within the core. So that is those are the major reasons why the accretion disk would be posing the young stars to be very unstable, and there are a lot of sudden brightness and fluctuations in luminosity that's taking place for young stars. So
Mobile
yes,
number?
the prime reasons are
Mobile number?
this is called the stellar
Hmm.
accretion process
Hmm.
primarily. And the
47.
stellar accretion process is basically nothing
Gadi
but
number?
the core is
Hmm.
undergoing a lot of
Hmm.
explosive reactions, nuclear reactions, nuclear fusions, fissions, all that's taking place there. And due to this accumulation of a lot of phenomena taking place there, there are a lot of jet emissions that's taking place to the outside. But at the same time,
गेट
these jet
कॉपी राखছে না
emissions are
বুঝলে
going
দিয়ে
out from the core. The
লিঙ্ক তো
rest of the
আর গেট
accretion
কপি
disk
রাখছে
is
না দিয়ে
being
দিচ্ছে
crushed by the the
দেখো
inward
দেখো
gravitational force. And also at the same time, it is also spinning very fast. It is also undergoing centrifugal force. So you can imagine the kind of pressure it has. There is a lot of jet emission going from the center. There is gravitational
आपका ना
force applied
आपका ना
from all the sides. And then the spinning also is creating the centrifugal force. So due to all these pressure, there is a lot of energy that is being bottled up and finally getting
ओ
released.
आपका
So that release is coming out as outbursts. Okay. So this was just an outline I wanted to draw to whatever we have already looked through in previous sessions. Now we'll have a project discussion on Hoy's and light curves. So, to know the importance of light curves and to know how to analyze them, it's always important that we know where these light curves come from, or uh, what stems these analysis. And developing a light curve, the light curve in itself may look a little technically complex, but the observational setup and light curve plotting through Abso tool might have given you an impression that it is a pretty simple job to do. So light
okay
curve generation in specific is not a difficult thing to do at all, since we have these softwares and tools to help us through. But whatever comes before that, that leads to the light curve generation, whatever data you accumulate, whatever data you observe, you try to procure, you try to throw in some procedure into it, as in storing, stacking, reducing, adding filters, and then finally coming up with a filtered superimposed image, and with that image trying to plot your data. That might be a little complex procedure. So as we sort of begin our steps as amateur astronomers, we'll try to learn how to dissect or analyze a light curve that we already have existing at this point. So yes, you will know what to do with a light curve if you get one. And later on, if you want to proceed with with these kind of projects, you can always try to try and plot a light curve of your own using tools or softwares or any manual procedures that you would like to undertake. So this was the second project I had discussed in my I think 2 sessions before, when I discussed about all 3 projects, major projects that you can do with amateur astronomy. So this project, the name is HOYS, or HOYS. The name is an abbreviation for hunting outbursting young stars. So you try to hunt the outbursting young stars. You see how the flickering patterns are. You draw a light curve out of it through various images and observations that you get, and you try to analyze these light curves. Moving on. So one of the only possible explanations for variability in a young star is primarily outburst, because young star is full of energy and it just doesn't know where to dissipate this energy. So all these energy are just emitted out like outbursts, in the form of outbursts. So when we perform something called a photometric analysis of such a star or a young star that is prone to have outbursts, the light curve plotted will have 2 possibilities, right? One is a sudden magnitude variability light curve, and then we have a periodic magnitude variability light curve. So if we have to discuss about the first one, okay, in detail. So during the outburst of a certain young star, okay, there are some sudden massive increase in brightness that we observe. And this increase in brightness will simply be analyzed using photometry. And you can observe it easily using a photometry because these outbursts on photometric analysis is very evident to observe. And the analysis of these collected photometric data can produce some further data when we change when we observe the change in temperature and there is an accretion date. So all these change in temperature and accretion rate increasing. So all these will give you some exponential rise in flux. So you might have learned from the previous activity we did in the previous session. We always look at the change in flux, right? So there is a brightness and time curve wherein you will be able to see how the flux have increased or reduced. For example, you take the value here and it at the end it is reaching somewhere here. So your flux increase is simply finding the difference, right? And so that's how you find your flux. And so these fluxes can be exponentially rising to a very higher number when there is a huge change in temperature as well as there is an accretion rate that is visibly evident, right? So that is when you have a sudden magnitude variability light curve. Coming to periodic magnitude variability light curve is when you see some sort of variation happening over a long time. It is not sudden, it is not momentous. So we have some distortions that is happening in the accretion disk, which is expected after the effect of outburst. So this light curve is what you observe shortly after the outburst has occurred, right? Now from after the outburst has occurred, everything is coming back to rest. So during the rest you see some sort of up and down movements, and then slowly it gains energy enough to go for another outburst. So whatever comes in between these outbursts is what we call a periodic magnitude variability, right? So such distortions that you see here cause some periodic fluctuations in the stellar magnitude that we observe. And even though some significant change, despite these factors, we will observe some significant change in magnitude. And this significant change in magnitude can suggest some, during this period before between the outbursts, there could be some formation of planetesimals. Can someone tell me what planetesimal is? We have discussed this term before. Can you tell me what planetesimals could be? Yes, I think we discussed about planetesimals um, during the discussion of formation of planets or
They're like
galactic evolution.
protoplanets.
Exactly. Protoplanets, another name is planetesimals. In simple words, planetesimals are nothing but like baby planets. They're infant planets, right? They're like a sapling that will further develop into planets later. But not, not all kinds of planets come from planetesimals. There are different ways of birth of planets. But planetesimals are primarily what leads to an exoplanet formation, right? So these graphs,
70
if you achieve, we will know that shortly there is a
74 85
planetesimal
level.
that is going to evolve into an exoplanet in a few 100 million years, right? So when this happens, some photometric analysis of these kind of periodic magnitude variability light curves will give us some insight on the radius of the exoplanets and orbital period, and some using change in magnitude of the star. So all these can give you some data on those kind of information. So these are the two kinds of light curve plottings that we predominantly find, right? Now, there are some very specific various techniques that is used for the discovery and characterization of celestial bodies in general. Some methods are
Simple
like
ना?
direct imaging. Okay, direct imaging is nothing but
Okay, बोलिए.
involving captures of some actual images that you're observing of the celestial body. And direct imaging is slightly more
4184.
challenging compared to the others because the light from the host star is much brighter than the light from the planet, right? So these lights can interfere with your observation, and it is this due to this interference, we don't primarily prefer direct imaging methods unless it is typically used for some studies about the celestial body that are relatively far from the stars. It is placed somewhere away from the host star and not interfered a lot with the boundaries of the planet that we are observing into. So these are predominantly for celestial bodies that do not give out light and also are placed away from light sources, right? And they also have wide separations between their atmospheric light interference points. Now, the next one is gravitational microlensing. Gravitational microlensing is utilized to find the gravitational fields of some very massive objects, primarily stars. And gravitational microlensing, as you can hear in the name itself, it'll act as a lens and it'll sort of magnify the light from the background star, and it'll emit that light, or they will try to shadow that light onto the object that you are trying to observe. So if a planet is orbiting the lensing star, or we call it lensing star, or the host star onto which the lens is pointed to, then it can produce some disturbances in the observed light curve. And these disturbances will particularly be useful for discovering planets that are that are in larger distances from Earth. And we can look into far away things, primarily with gravitational microlensing. Also, it has to be, as opposed to the direct imaging part, it has to be fairly closer to the star's vicinity, so you can point your lens towards the star and take maximum light input and shadow that light input onto the celestial body that you're looking into. And next we have astrometry. Astrometry will involve measuring some small shifts in the position of a star, and these small shifts could be due to some gravitational pull of an orbiting planet. And these pull can produce some sort of variations, and these variations can be noted. And astrometry is primarily to note how the movement or orbital movement of certain celestial bodies are. And during this orbital movement also, rather than just calculating how it behaves in an orbit, it'll also calculate how it behaves within itself due to the effect from outside, from the surroundings as well. And we have ESAs, or European Space Agencies Gaia satellite. I don't know if you've come across the term Gaia satellite. Gaia is a very famous ongoing project that's been ongoing for a while now. So Gaia D3, Gaia project in general is a specific kind of satellite working to make astrometry more convenient for observation. So the satellite is used primarily for astrometric exoplanet detection in specific. Then we have TTVs. TTVs is nothing but transit timing variations, and this is primarily a technique that looks for certain deviations in the timing of transits of the body when it goes around the host star. And when it transits around the host star, it causes some sort of gravitational interactions with other planets in the system. And this gravitational interactions can cause the other planets to, have certain shifts from what they are, or certain shakes because of the gravitational pull. So those other planets that is affected by the gravitational pull of certain planets can be observed with astrometry, while in the planet which may be causing the shift can be looked upon through TTVs or transit timing variations. Then we have pulsar timing. So pulsar, as you can hear by the name of pulsar timing, it is just pulsar signals are nothing but periodic signals that goes in a stagnant, constant way. It'll be more like a sinusoidal curve wherein it just goes like it'll just pulsate like a heartbeat, right? So pulsar timing will involve some observation of pulsar stars, which will give you data that is similar to ECGs of heartbeats. That is very similar to those. So you will be getting some pulsar timing data of pulsar stars. So pulsar stars are nothing but some neutron stars that are rotating, and it is emitting certain regular radio pulsar waves or pulsar signals. So these pulsar timings can be recorded and can be known, and these pulsar timings can tell you what is the vicinity of that particular star, or what is the kind of forces that is applied onto the star, or what are the emissions that is taking place on the star. And any variations in these kind of pulsar timing can be suitable for discovering other planets that is surrounding these pulsars as well. That is how the vicinity is giving you a picture about it. Then we have eclipse timing variation. Eclipse timing variation is similar to TTV, and just like TTV, more like TTV. If TTV was looking into transit timing variations, it's more like a clubbed thing, right? TTV is looking at to any kinds of transit timing. Now, ETV is specific onto a variation in the timing of eclipses that take place. So basically deals with shadow casting than light falling, right? And then we have microwave and millimeter wave detection. Now, here in microwave and millimeter, you can clearly understand there are two values put here. Microwave is a kind of radiation, and millimeter is kind of a dimension, right? So here the observations will be based on EM spectrum, because EM spectrum deals with these kind of radiations, and that is electromagnetic spectrum. And these observations are very sensitive to very sensitive to some thermal emissions of the planet, and can provide information about their atmospheric properties, their temperature fluctuations, and any kind of thermal related observations can be made using an M&M wave detection. And we have atmospheric characterization. That is atmospheric characterization, apart from all of the above, is a spectroscopy, and wherein we were dealing mostly about photometry in all the previous processes that we were talking about. Now, this is more of a spectroscopy of exoplanetary atmospheres. So, atmospheric characterization will be giving you atmospheric composition details of exoplanets in specific, and it will analyze the absorption and emission features of the spectra. And through these absorption and emission fields, you will be able to get a sort of an emission curve or emission field line, and you will see where all the blinds are coming, where all the space in emission lines are coming. And this will gain insights into the chemical composition, and through what all the light or the radiation is able to pass through, what all components it is not able to pass through, or at what density it is able to pass through. So these will give you the chemical compositions and some physical conditions of the exoplanetary atmospheres that you can look through this. Then we have the phase curves. So phase curve observations will involve some sort of, studying the changes in the exoplanet's brightness, various phases, how the phases appear. So these phases would be about the brightness phase, how the changes in brightness as it orbits around the host star, and various other phases like emission phases, etc., will also be covered here. And these observations can, provide some sort of, idea about the planet's temperature distribution and atmospheric properties to a limited way, wherein atmospheric characterization will give you detailed about the composition and the limits and the percentage, the density, etc. Now, phase curves will give you an idea of detection, whether it is there or not. So that is about phase curves. Now, radial velocity confirmation. Now, radial velocity is also, so now, the last two that you see are specifically most commonly used for exoplanets, and these are the two, especially transit photometry, but radial velocity and transit photometry is what is primarily used for any methods of looking into an exoplanet. Whether we do all the other processes that you see are on a need basis. If you want to look at a direct image, and if you want to get your observations from an imaging source, then you go for direct imaging. If you want atmospheric composition, you go for atmospheric characterization. You want radiation details, you go for microwave and millimeter. You want transit details, you go for TTV. You go for any orbital shift or position shift, you go for astrometry. So those are need basis based on your research, or you can adopt the kind of method you want to approach. But radial velocity and transit photometry are some basic processes you need to run for any kind of observation you're trying to make here. Like if you want to follow astrometry, or if you want to go for any TTV or MNM, any of these procedures have to first undergo transit photometry at the basic level. And if you want run a spectrometry through radial velocity as well, and then you step into any other kind of observation that you would like to go for. So radial velocity is primarily used for exoplanet detection, as I've mentioned earlier. And it is also, it is a very important factor. This radial velocity is a very important factor to confirm the existence of an exoplanet on the first place. So to confirm the existence of an exoplanet, you can use radial velocity, and then you can go on to use any other methods, and you can go for the basic transit photometry. So when I say we have worked on a certain project on certain exoplanet, this is because due to the characterization, I understand that it was an exoplanet and I would like to work more on it. But people before me have categorized it as an exoplanet because they have done radial velocity and confirmed the existence. So they have already done radial velocity, confirmed the existence of so and so exoplanet, and left it there. Now, when I was doing my project, I had took up those already known exoplanet which has already undergone radial velocity and confirmed its existence. Then I've taken that up, conducted my transit photometry, and then you leave it there. Now you have number of opportunities to simply conduct radial velocities of certain celestial bodies, confirm whether it is an exoplanet or not, record your observations, put it into a portal that is globally activated under various space agencies. It will be under your name, and people from around the world, scientists from around the world, when they, astronomers from around the world, when they want to do further studies on this particular exoplanet, they will go back and look at your radial velocity mapping. Right? So this is the major idea of radial velocity. And each of these techniques that I've discussed here has its limitations and has more strengths as well. And they are often used in combinations to get more accurate data. Because just by doing TTV, you may have one data, you cross verify it using an ETV. Then when you do some sort of what do you say, then if you're doing TTV, you also try to do an astrometry, so you can confirm whatever shift is happening an opposite reaction is happening on the neighboring planet as well. Then when you do an atmospheric characterization, you also try to do some sort of phase curves. So the phase curves will give you some sort of, details on these kind of atmospheres are there or not. So it always is better if you do it in pairs. You can also, take the values of one and affirm it when you do your second uh, method of light curve development. So yeah, combinations will help you to understand your the systems that you're observing in a bit more comprehensive way, and you can be sure of your results if you cross check it through a couple of methods. Now we go to the major question or major idea that a lot of us still have confusions about. Now, photometry and spectroscopy or spectrometry are some very fundamental techniques in astronomy that is used to study some celestial objects and gather some information about their properties. The main idea of photometry and spectroscopy is photometry, as the name suggests, you can remember it this way. Photometry is about the light's intensity. So it always deals with brightness, luminosity, anything that has light will undergo a photometry, or anything that has light is involved in your observation, still it will go photometry. Like, for example, you observe at a light at an exoplanet transit, right? You try to do a photometry of an exoplanet. Exoplanet in itself doesn't have any light coming. So photometry is a method wherein you try to run the exoplanet in front of a star. The light from the star will tell you how big the exoplanet is, how much of the exoplanet, when it passes through the in front of the star, how much of the exoplanet is covering the star, that much you will be able to get the information like that. So whenever there is some sort of light source involved, or there is a light or brightness check involved, then that is called a photometry. Spectroscopy is when you check the spectrum, mostly deals with the radiations, waves, signals, uh, areas, compositions, etc. That is what spectroscopy deals about. So you can remember it that way. And photometry in detail, just to give you, because we are looking more into photometry than spectroscopy in our sessions. So I'm trying to give you a little more idea about photometry. As I've mentioned, it is a measurement of light intensity, and for various, what do you say, for different variable stars, right? Variable stars, young stars, all of that. We use photometry to track the changes in their brightness over a long period of time. And whatever the resulting data is, that resulting data is visualized in a more comprehensible manner through the help of a light curve. And this light curve is very crucial because for a certain period determination, or the transit time that is taken, the duration of the transit, all of these will give you a very important outlook into your light curve. And it will classify some variable stars, it will classify various trends on the variable stars, it will give you ideas about how much of a variation is happening up over how much of a time, what is the flux that is taking place. All of that will be given through a light curve, which is done through photometry. All right, so here we come to the key factor of this session, that is the light curve. Now, some of the key features of a light curve include maxima, minima, periods, and amplitude. Now, maxima is what you see here. Minima is this. Period is when traveling from one maxima to another maxima, or from one minima to another minima. Okay. And what is the other one? Amplitude. Amplitude is this height up to what your maxima goes. That is your amplitude. So maxima is also called something called a brightness peak. Okay. Up to what peak your brightness will go. So maxima, minima are more of a graphical language, or language that we follow in graphs. But when you have your, if when you discuss in project terms, you say brightness peak, brightness troughs, And the period is nothing but the time it takes to complete one whole cycle. That could be two brightness peaks or two brightness troughs. And amplitude is simply the maximum that the brightness peak is achieved, or simply the difference between the maxima and the minima, right? So this is a sample, light curve observed on Pluto. So this is just for your understanding. So this is a sinusoidal curve that we observed on the magnitude. And we can see that the brightness peak is going up to this much, and the brightness trough is going up to this much. There is you can do a lot more observation on this. You can find the amplitude, what is the flux change, what are the various factors that you can consider here. All of that can be taken. Now, a fun question. I think so many of you have, uh, understood why Pluto is no longer a planet in the solar system. Can someone tell me what your understanding is about?
Because it's too small for size of a planet.
No. Pluto is approximately the same size of Mercury. And we do have exoplanets smaller than Mercury, which could be, around the size of Pluto. So size is not the problem. Any other factors?
The Pluto is actually very smaller than Mercury and Moon. So
Yes, it is smaller. That's why I told we have planets that are smaller than Mercury, and which is around the same size of Pluto. We do have exoplanets of that size. So it can still be categorized as a planet. But size is not a primary factor. It could be a factor, it could be a supporting factor, but size is not the primary factor.
most of Pluto is made of ice. So if it were where Earth is right now, it would the ice would evaporate and it won't resemble a planet.
Again,
Something like that.
that is about the composition. Okay, in that case, your gas giants are mostly made of ice. It has a lot of icy components. It has a lot of icy. There is an entire ice belt, like a Kuiper belt, after Neptune. So yeah, those planets also are extremely away from sun, and they are pretty icy. They have very low temperatures. So again, temperature is not a problem. Okay, let's categorize. Pluto is not able to be uh, qualified as a planet. What are the various qualifications required for a planet?
It must have an elliptical orbit around the star.
Okay, Pluto is still revolving around the star. Tick.
But
All
it
right.
crosses another planet's orbit.
Sorry?
Crosses another planet's orbit.
Yes, it does. Exactly. So, one major criteria a planet has to qualify is its vicinity has to be clean. It shouldn't have other celestial bodies or any kind of uh, planet light. It can have moons around it, okay? But it cannot have any sort of planetary debris around it. So, since it is crossing or it has other planets in its vicinity or in its orbit, is why we are not able to categorize Pluto as a planet in itself. Got it? It'll be more like a moon. Hope you've got the idea. So there are a lot of versions going on. So if you sit and analyze it, you'll be able to strike off a lot of properties out of it. And one of the few properties that will remain at the end is that Pluto is more qualified as a moon than a planet because of its vicinity. Hope that's clear.
Yes, ma'am.
All right. Okay. So that is about light curve. That was a quick iteration I took. Sorry. And we have some about spectroscopy. So spectroscopy, as I had mentioned, is okay, we are crossing the time. Okay, I think I'll take the rest of the session in the rest of the session in the upcoming session. Then I will look through this on Friday's session. We don't want to extend the time. All right, so we'll continue the session from spectroscopy in the upcoming session. And once we discussed about spectroscopy, and then we'll have a detail about transit photometry, we'll get into the project discussion. You will have a live solving manual calculation on sample stars light curves. You will be observing and you will be solving it in the class, and we'll be discussing about the results, and we'll be trying to plot it on the HR diagram, as you all remember from before. So this is the plan for this session. Anyway, since we are running out of time, I think we'll take this session up for the next one. Yeah. Is everyone cool with that?
Yes, ma'am.
All right, all right. So please make sure that you attend Friday's session. We'll be looking into the rest of this portion in the upcoming session. So if that's all, we'll call it a day. Yeah. Thank you. Thank you, everyone. Good night.
Thank you, ma'am. Good night.
Thank you. Good night.
Thank you, madam. Good night.
Yes, Akshit. Yes, you wanted to ask something?
Yes. Yes, ma'am. Can you
Yes, Akshit.
provide the link for the previous sessions?
Yes, Akshit. Definitely, you can contact Mriganka, and he will have all the class recordings.
Yeah. And I
Okay.
have a doubt that what should I do for to keep up with the group and everything that you have covered till 1 month?
Okay, so we have had a lot of assignments previously done. So, if since we have already completed the assessment of those assignments, it would be unlikely to put it along with the assignments. But if you're interested, you can separately start doing assignments looking at the recordings, and you can submit the assignments personally to me. I can help you through the assignments, as in I can analyze it, assess it for you separately, and if you would like some feedback on it or more guidance on those assignments, I can provide you separately. I doubt if I can put it along with the rest of the batch,
Okay,
because we
ma'am.
have around 2-3 months worth of assignments already. So I'm not sure if you'll be able to complete all of those in one go. So I would suggest that you can go through the recording slowly. You can try to do your assignments as you go with the recordings, and you can contact me separately and we'll discuss about the assignments. Okay.
I have another doubt that if this subject is going to be covered up to 6 months, overall 6 months,
Um,
or it has a different timetable. I have no idea about it.
Actually, yeah, this batch had started in September. Is that right, Samali?
Yes, ma'am.
Yeah, so it is 6 months from September that the rest of the batch is covering. So I believe you joined in November, Akshit.
Yes, ma'am. I joined in November, and I was in
Okay,
a November group in which Samira ma'am and Karan sir was used to teach the subjects.
all right. Was there anyone else who took astrophysics?
Then there was no one. There was only four subjects that aerodynamics, avionics, propulsion, and structure.
Okay, all right, got it. Okay, so in that case, you can follow the recordings. you will be lagging by 2 months, if I'm not wrong. But for the rest of your 6 months, you can start going through the recordings for astrophysics. If there's any guidance or any explanation on any topics that you require, you can come up and check with me. Also, if more people from your batch are joining astrophysics, then I believe we will be having sessions for you guys, full-fledged live sessions. If not, I believe you will be following the recordings.
Are there any more groups up to different subjects that
Sorry?
I'm more interested? Is there any more groups of different subjects? Actually, I'm more interested in avionics subject actually.
Okay, all right. So you can talk with your coordinator and you can because I primarily take only astrophysics sessions. So I think avionics is taken by Samira or
Yes, ma'am. Samira, ma'am. By Samira, ma'am.
yeah, okay. Yeah, so you can check with Samira as well as you can check with your coordinator. So you will be getting more sessions on avionics, and if you're interested, you can join the astrophysics batch as well. That is up to your interest.
Okay, ma'am. Thank you.
No problem. And if you're planning on looking into the recordings, you can let me know. You can find my number in the WhatsApp group and you can contact me separately and you can, any sort of guidance is appreciated. Yeah.
Okay, ma'am. Can you send me the number because I don't know which was it.
My WhatsApp number?
Yes, ma'am.
Sure, I can put it on the chat. Problem. Yeah, this is my WhatsApp number. You can also
Okay, ma'am.
contact me via mail.
आपका कॉपी
Yeah, this is my mail ID as well.
Yeah, ma'am.
All right. Yeah, you can better note it down because once I end this meeting, you may not be able to get it.
Yes, ma'am. I noted it.
All right. No problem. Okay, that's about it, Akshay. Thank you for joining the session. Hope to see you more in the upcoming sessions. That is if you're interested. No forces here. So you can talk to
Yes, ma'am.
Samira
Yes,
and you
ma'am.
can talk to your coordinator as well. They will guide you on how to go forward with the sessions. Yeah.
Okay.
All right. Thank you, Akshay.
Thank you.
Yeah. Brishaketa Bera, do you have any questions?
मैम
Hello, Brishaketa Bera.
एप्सो ऐप
You were saying something?
No, Akshat, I was talking to the other person in the call.
Okay, okay, okay.
Yeah. Okay.
It's